one of the questions that motivates our study of groups is to be able to distinguish when two groups are isomorphic and when they aren't isomorphic. So suppose I give myself two groups, G and H, and I'm asking, so what properties of G and H would tell me that they're not isomorphic? So when is G not isomorphic to H? When G and H are groups. So we already know a few cases when this happens. The first one is when the order of G is not equal to the order of H. If G has 7 elements and H has 9 elements, I know they're not isomorphic because there's no bijection between sets with different number of elements. So, boom, that's done. Okay? If your groups that you're looking at have different number of elements, you know they're non-isomorphic for sure. Sometimes, however, you have groups that have the same number of elements, like the example we looked at, Z mod 4Z and Z mod 2Z cross Z mod 2Z. Both of these groups had the same number of elements, 4. However, we have this more refined case where if we can count how many elements of a given order G has, then H, if it's isomorphic to G, should have the same number. So when G has a different number of elements of order n for some n, than H. So, for example, if I'm able to find, say, some number 5, and I compute how many elements of order 5 are in G, and then how many elements of order 5 are in H, and it's a different number, then I know for sure G is not isomorphic to H. That's one of the properties we proved. The problem with this criterion, it's really great, it's really a good criterion, except for some groups it might be very laborious to count the number of elements of a given order if the groups are big. And secondly, sometimes it just isn't that useful when you deal with infinite groups, for example. So in particular, when you think about Z with addition and Q with addition, they're both infinite groups, so they certainly pass the criterion that their orders are the same, both are infinite. But secondly, how many elements of order 1 do I have in both? 1. In every group there's only one element of order 1, namely the identity. So 0, because we're looking at addition here. And what are the orders of other elements? We looked at this already. Every other element in Z has infinite order. But similarly, if I look at Q under addition, then the same is true. Every other element in Q other than 0 has infinite order. So they have the same number of elements of order 1 and then the same number of elements of infinite order, and they have no elements of any other orders. So it's completely unhelpful in this case. There is yet another criterion that we talked about last time, namely we proved that if you have a surjective homomorphism from G to H, then when G is abelian, so must be H. And if G is isomorphic to H, then this isomorphism is of course a surjective and injective map, it's a bijection. So if G is abelian, then H must also be abelian if they're isomorphic. So if I'm looking at two groups and they have the same number of elements, and I'm somehow not able to apply this criterion, and G is abelian but H is not, then I know they're not isomorphic. There is yet, however, another, so look, this wouldn't have worked for this case, right? Because both Z and Q are actually abelian. So none of these actually works to be able to distinguish if these two groups are isomorphic or not. So there's yet another criterion that you can use, and that's the criterion of cyclicity. So cyclic groups is a topic we're going to be spending quite a lot of time on. So to do this, to study cyclic groups, we have to define what a generator is. So definition. Let G be a group, and let X be an element of G. Then X is called a generator, G if every element of G in G can be written as G is equal to x to the m for some integer n. Again, I remind you what that means. When n is positive, that means I multiply x that many times using the binary operation in the group G. If n is negative, I mean I multiply the inverse of x that many times. And if n is 0, that just means the identity. So if in a group there's just one element, such that every element in the group is a power of that element, then such an element is called a generator of G. It's called a generator of G. And a group that possesses a generator is called cyclic. And we will see that that's another criterion that can be used to distinguish groups that are not isomorphic. That is, if G is isomorphic to H and G is cyclic, so is H. Okay? But we first have to prove some things about this before we get to such a statement. So let's start with examples. One, Z mod 7Z is cyclic. Namely, let me introduce a notation here. A group that possesses generator is called cyclic if X is a generator of G, we can write G is equal these angle brackets X. That means somehow that X, this one element, generates all of the group G. Okay, so I claim Z mod 7Z is cyclic, so I have to give you a generator. So namely, 1 plus 7Z is a generator. So really, can I get every element of Z mod 7Z as a power of this? Now, what does it mean in this case to be a power of this element? The operation here is addition. So to be power of this element means that I'm adding this element enough times to itself. In other words, I'm multiplying this element by some integer. But that's clear, right? That every element is a power of this. So 2 plus 7Z is 2 times 1 plus 7Z. In other words, I need to add this twice to get to this element. 3 plus 7Z is 3 times 1 plus 7Z. So if I take this element 3 times, I get this. And so on, right? A plus 7Z is A times 1 plus 7Z. So yes, this element is a generator, so that group is cyclic. So I could write Z mod 7Z is equal to 1 plus 7Z. Even though exhibiting one generator for a group is enough to show that it's cyclic, in fact, a cyclic group can have more generators than just one. So an interesting thing to notice about this group is that, in fact, every non-zero divisor in this ring would be a generator for this as a group. So let's just try 3 mod 7Z. So I claim that this group is also equal to 3 mod 7Z in brackets, so that this is also a generator. So can I get to every element from using 3 mod 7Z? So how do I get 2 plus, well, let's just keep exponentiating this. So if I take twice 3 mod 7Z, 3 plus 7Z, then I get 6 plus 7Z. If I do it 3 times, That's 9 plus 7z, so 2 plus 7z. If I take it 4 times, not 4 but 3 here, then I get 12 plus 7z, but 12 plus 7z, that's the same as 5 plus 7z. 5 will give me 15, but it's just 1 plus 7z. Well, once I actually get to 1 plus 7z, I already know this is a generator. So if I just take multiples of 5 times 3 plus 7z, I can get everything. But since the list isn't so long, I can just do this one more time. So 18 plus 7z, that's 4 plus 7z. So you see, I can get every element, right? 3 plus 7z. So 1 plus 7z, 2, 3, 4, 5, 6. How do I get the identity? Well, I'm allowed to take the 0th power. I'm allowed to take any integer power, so that's also 7z. So I get to every element. So this is a generator, this is a generator for that group. In any case, it's a cyclic group. And in fact, it's not that difficult to prove that z mod nz is cyclic for every n greater than or equal to 2. And what's a generator? One plus nz will always be a generator, no matter what n is. Because if I take it twice, then I get 2 plus nz. 3 times I get 3 plus nz, so this way I get every element. And if I take that 0 times, I get, of course, nz. So I get every element. So these groups are always cyclic, the z mod nz. Let's look at z with addition, and I claim that this group is also cyclic, and in fact it's generated by 1. So is every integer a power of 1? But remember what power means in this case. The operation is addition, so power just means multiple. Is every element in z a multiple of 1? Sure, yep. How do I get n? I just do n times 1. It could be negative as well, right? N is allowed to be negative. So, I mean, the exponent is allowed to be negative. So how do I get minus 5? That's just minus 5 times 1. There's another generator of z, namely minus 1. From minus 1 you can also get to every integer by multiplying it by some integer. But that's it. These are the only two generators of z. If you take any other number, say if you take 2, then if you take multiples of 2, you only get the even integers. You do not get the entire group. But to be cyclic, it's enough to have just one generator. So z is cyclic because I found a generator for it. Let's look at q. With addition, I claim q with addition is not cyclic. Well, how do I know that? So let's prove this by contradiction. So suppose q is generated by some rational a over b, and a is not 0, b is not 0. I mean, obviously q is not I can obviously assume that a isn't 0, because if a is 0, then a over b is 0, and 0 doesn't generate anything. Any multiple of 0 is still 0, so for sure it doesn't generate q. So I can assume that these are not 0, and I can also assume that the GCD of a and b is 1. So in other words, this fraction is written in shortest terms. So if this is the case, right, so that means then every rational number, every alpha in q, can be written as, okay, a power of this, but again, the operation here is addition, so power just means multiplication. So it's n times a over b. But this is nonsense, right? I cannot get that. So for example, so this is nonsense. Since I cannot get 1 over b plus 1 this way. Yeah? Suppose that maybe this b was 5 and the a was 2. If I just look at integer multiples of 2/5, I can never get anything that has a higher denominator than 5 and numerator 1. Right? I cannot get 1/6 from multiplying 2/5 by integers. So no matter what the generator were, it has some denominator b, and then I can never get 1 over b plus 1 from this. Okay, so Q is not cyclic. So once we prove that if G is isomorphic to H and G is cyclic, then H also has to be cyclic, then we will know that Z is actually not isomorphic to Q as a group. All right, another example, 4. Z mod 2Z cross Z mod 2Z is not cyclic. Well, all right, here I can just sort of check it by hand. I can take every possible element of this group and see if its powers give me everything. Because that's what it means to be cyclic. There is an element whose powers give you everything. 0, of course, 2z comma 2z is non-starters, so let's try to do 1 plus 2z, 2z. Okay. What happens if I take the twice? Again, the operation here is addition of congruence classes, so the exponentiation turns into multiplication. So if I do that, I get 2z, 2z. Oh, so 3 times that will be again 1 plus 2z, 2z. 4 times that will be 2z, 2z. And I'm only cycling between these two elements. 1 plus 2z, 2z, and 2z, 2z. So this cannot possibly give me all the elements of the group. What about something else? Like maybe 1 plus 2z, 1 plus 2z would do this. So if I do twice that, I again get 2z, 2z. So I run into the same problem. Taking powers of this only gives me this element, and then this element, and this element, and this element, and so on. I'm just cycling again in that pair. And you can also check that the last one, so 2z comma 1 plus 2z, also doesn't work. So none of these generates the entire, every element in the group. So there is no generator in this group. Okay, so let's actually prove something about cyclic groups. Let's take a little break and prove it in the next video.